Okay, say the name Archimedes. What's the first thing that pops into your head? It's a guy in a bathtub, right? Yelling Eureka. But what if I told you that famous story, the one we all know, isn't really the whole picture? Yeah, in fact, it might not even be the most interesting part of the story. Let's dive in and see why. Well, they're all connected by one of the most fundamental laws of physics, a principle that's over 2,200 years old, and believe it or not, it's still hiding some really surprising secrets. Stick with me, and by the end of this, you're going to see exactly how all these pieces fit together. All right, so first things first, let's tackle that story that pretty much everyone knows. You know the one. It's got a bathtub, a king's crown, and a very excited and very naked mathematician. So the legend goes like this. King Hero of Syracuse gets this beautiful new crown, but he has a sneaking suspicion it's not pure gold. So he gives Archimedes a challenge. Figure it out, but you can't damage the crown. And the solution supposedly just hits him. He's getting into his bath, sees the water level rise, and in this flash of genius, he takes off running through the streets, naked, shouting, "Eureka! I found it!" But, and this is the big but, here's the twist. That amazing Eureka moment, it wasn't really about figuring out why things float. Nope. The real breakthrough was that Archimedes realized he could use the displaced water to measure the crown's volume, an irregularly shaped object. Once he had the volume, he could compare it to its weight, calculate its density, and boom, he'd know if it was pure gold. It was an absolutely brilliant solution, for sure, but it's not the Archimedes principle that we all learn about in school. Okay, so if that whole bathtub story was really about density, then what is the actual Archimedes principle? You know, the one about buoyancy. Let's get to the real heart of it. So here it is, the formal definition. It's really one of the cornerstones of hydrostatics. And what it boils down to is this. When you put something into a fluid, you know, like water, the fluid pushes back up on it. And here's the crucial part. The strength of that upward push is exactly equal to the weight of the water that got shoved out of the way. Let's just walk through that one more time. Step 1, an object goes into a fluid. Step 2, it pushes some of that fluid out of the way, right? It displaces it. Step 3, the fluid pushes back with an upward force. We call that the buoyant force. And step 4, the big insight, that upward push, that buoyant force, has the exact same strength as the weight of the fluid that was displaced. Simple as that. So what this sets up is basically a battle, a tug of war between two forces. You've got the object's own weight pulling it down, thanks to gravity, and you've got this buoyant force pushing it up. So who wins? Well, it all comes down to density. If the object is denser than the fluid, it sinks. Down it goes. If it's less dense, it floats. Up it comes. And if the densities are perfectly matched, well, it just kind of hangs out, perfectly suspended, in equilibrium. And this one single idea explains so much. Think about it. How does a massive ship made of steel, tons and tons of it, float? Well, it's mostly hollow, filled with air, which makes its average density less than water. So it floats. In a hot air balloon, it's the exact same principle. The hot air inside is less dense than the cooler air outside, and that difference creates lift. It's the same rule, just one is in water and the other is in the air. Okay, so far so good, right? It all seems pretty straightforward. Denser things sink, less dense things float. Simple. But this is where our story is about to get really, really weird. Because the question isn't just if something floats. The real question is, how does it float? I want you to picture something. Imagine a long wooden log, and its ends are perfect squares. Now, if you toss that in the water, how would you expect it to float? Flat on its side, right? Seems obvious. Well, turns out it depends entirely on its density. Okay, so let's say we have a really light log, maybe one with only about 20% the density of water. In this case, everything works just like you'd think. If you try to push it over, to tilt it onto its corner, the buoyant force creates this twisting force. It's called a torque. And that torque immediately pushes it right back to a stable, flat position. Easy enough. So far, so simple. But now, watch this. What happens if we use a denser log? Let's say one with half the density of water. All of a sudden, floating flat is unstable. It doesn't want to do it. The tiniest little nudge creates a torque that, instead of pushing it back, it actually pulls it over until it settles into a completely new, perfectly stable position, resting on its corner at a perfect 45-degree angle. How weird is that?
Oh, but it gets even stranger. At one very specific density, around a quarter of the density of water, the log does something else entirely. It doesn't settle flat, it doesn't settle on its corner. Instead, it finds a stable, balanced position at this bizarre, what seems like a totally random angle of about 27 degrees.
So what on earth is going on here? Well, it's because the log's density changes the shape of the water it displaces, and that change moves the center of the buoyant force around. This creates these weird torques that can pull the object into these strange but totally stable positions. It's not chaos, it's this incredibly beautiful and complex dance between gravity, buoyancy, and the object's shape.
Okay, so just to recap, we've gone from the myth of the bathtub to the real physics, and then into its truly strange complexities. And for our final act, we're going to take a huge leap and see how this ancient principle inspired a modern and pretty controversial piece of theater.
This quote, it really gets right to the heart of a play called, you guessed it, The Archimedes Principle, written by the Catalan author Josep Maria Miró. And it does something incredible. It uses the very same physics we've been talking about as a powerful metaphor for how we behave as a society. The plot itself is, well, it's unsettlingly simple. There's a swimming instructor, and he comforts a crying kid who's scared of the water. He gives the child an affectionate gesture, a hug, but someone sees it, and a rumor starts to spread among the parents. And here's the key. The play never ever tells you what really happened. It's not about the truth. It's about the powerful, corrosive mechanism of suspicion itself. And this is where the physics comes in as a metaphor. The instructor, he's the object, but he's not being immersed in water. He's being immersed in a fluid of fear and paranoia. And that upward buoyant force, that's the rising social pressure, the whispers and the accusations that threaten to completely destroy his reputation, whether he's innocent or not. So think about where we started, a 2,200-year-old law of physics. It doesn't just explain why a giant steel ship can float or why a log tilts at a weird angle. It can also be used as a lens to understand how an entire community can turn against one of its own. It's just a powerful reminder, isn't it, that the fundamental rules of our universe can echo in the most unexpected places, from a bathtub in ancient Greece all the way to the complex and sometimes dangerous social pressures we face today.